climate discussion seminar.
Climate discussion.
We're getting close. Well, it will be a discussion of climate.
Will you discuss the climate?
Yes.
Yes.
So many of you know our speaker today, Professor Jagadish Shukla. He is a distinguished faculty member in the AOES department here at GMU. He is also the founding chairman of the AOES department. And if you were to look over Shukla's CV, you would find the word chairman used a lot. Just to name a few, he of course founded COLA. He established the Ghandi Women's College in India. He founded IGES. He helped establish a numerical weather prediction center in New Delhi, amongst other things. So, in recognition of his contributions to the field, Shukla has received numerous accolades from the community. We could spend half the seminar time talking about that alone, so I'll stop there. And these special honors were in acknowledgement of Shukla's contributions to climate predictability. And I'm quoting from the Shukla Symposium biography, but during the 1970s, the fundamental belief in predictability was framed within the context of the butterfly effect. And so the community really believed that there was a fundamental limit to our predictability, and that was about a 2-week time period. And Shukla work led to the notion of predictability in the midst of chaos, which was the theme of the symposium, and it laid the groundwork of the development for the scientific basis for climate predictability. And so today we're fortunate enough to have Shukla talk to us about the dynamic seasonal predictability and the monsoon and the monsoon and ENSO relationship. So thank you all.
Okay, thank you. So now we know why we give this seminar, so we can to hear about yourself. I see. This is nice to do. But thank you very much. That actually, I'm so glad you mentioned about the predictability in the midst of chaos, because that basically drives some of the talk, today's talk that I was going to give. I'm really, so thank you all for coming. I'm especially grateful to our colleagues from Geology Department who are here, and one of them threatened me I'm coming, so I immediately went and changed all the TLAs. You know what TLAs is? 3-letter acronyms. I changed them all to expanded them so that I can describe. Anyway, I just did. So, and of course, I have to thank a lot of people. I have talked to them, they have given me diagrams, they have given me. But actually, it's not enough to just thank people just in a small slide. So, everything I've done in the last 25 years, I really owe to all my colleagues in COLA. So I should really have another slide to thank everybody, which is this, because I mean, these are the people that have worked from 35 years, some people for 25 years, and some people for 15 years. So anyway, thank you all. This has been, I had to give a seminar at NASA, so I thought this is one way I can thank all my colleagues. So the outline of the talk today. First of all, although I'm going to talk about some science of predictability of seasonal averages, I thought I'd take an example of Indian monsoon forecasting, and it sets a very good example and tell you what is happening, how it started in 1875. It's not a typo, it says 1875. So this is the longest time scale we go, by the way, in our seminars. So then I will give a, so this is so nice. That's what I say, your introduction is so nice. Because when I accepted the invitation, I thought I'll have a hot result to talk about. Sorry, and I told her, but if I don't, I'll tell stories. And so I'm going to tell stories. One of the stories is dynamic seasonal prediction. This is the thing that's mentioned. How did we go from butterfly effect to predictability? So I'll just give the personal retrospective for a few minutes. And then I will summarize the results of an actual prediction experiment that has been done by Huang et al. It has already been published actually. I'm so glad to say that the paper just came out. And then I'll pick from that two examples, two biggest El Niños that we have seen. So and then explain to you what are the challenges. Because we find a high predictability but low predictability. So how to bridge that gap? That's the sort of. So let's just go. I'll be, as I say, when I found out that we have colleagues and also a lot of students, I thought, okay, I'll take a few minutes to describe the basic monsoon. So let's see, where was the slide you gave me? You just gave me a PowerPoint. What did I do? Yeah, the pointer you gave me. So, all right. Oh, you have it. Oh, you did give me.
Yeah.
No,
I don't know how I ended up with
Okay,
it.
so just remember some basic facts about climatology. During the winter season, the rainfall maximum is in the southern hemisphere. Okay? And so is the sea surface temperature maximum, the warmest water source. So it's sort of, it already suggests to you that sea surface temperature is very important in determining climatology. This is in the winter. Then in the summer, this whole warm water moves north. Now you see the warmest water is in the north. And now look at the rainfall. And so this is the monsoon season that we really work on very hard. But I wanted you to remember always the seasonal cycle, because everything we are talking is superimposed upon that. For those of you who may be asked in your PhD exam, what will happen to monsoon if sun was not there? This is always asked. Normally we say that, okay, sun heats the land, and that's what causes monsoon. This is sort of the giant sea breeze effect. What Mike Fennessy is not here, he did many years ago, that he did a numerical experiment and say, okay, I'll keep moving the sun, but I will not move the SST. Guess what? You don't get a monsoon. Or you just keep moving the SST, but don't move the sun. As you can imagine, this is a hypothetical, so this is a good thing about models we can do. So it's both the northward propagation of the solar forcing, which causes also, and that's one of the biggest problems with a couple of models, is that they don't do that propagation very well. So I think just keep that in mind. But ultimately, we are going to talk about the Indian summer monsoon. So I have to sort of ask you to train your eyes. Now, here is the problem for India and for all of us as meteorologists. Here was the monsoon rainfall that India is interested in, but look at the Himalayan mountain ranges. So the dynamical effect of orography, both the barrier effect and also heat source effect. We have a heat source right at 5 kilometers. It has a huge impact on the monsoon, and the net result is that the mean rainfall in the summer monsoon looks like this. So this is climatological rainfall, and it's such a deep structure. So I just want to let you know that this is a challenge for us, our models, to capture it. Important thing is that most of this rainfall is over ocean, where we don't have data. Okay, and I'll come to that in a moment. The big shadow region, there's no rainfall, and there's another big rainfall maximum here, south of the equator, where every model gives completely different results. And so these are the challenges that we have in getting the, but so keep that in mind. So why monsoon is of so much interest? I'll just give two reasons. One scientific and one sociological. Scientific is very simple to understand. This is the summer monsoon, summer season, temperature and wind. Look at that. The warmest temperatures are at 30 degrees north. Is it not strange? Equator is supposed to be warm and poles are supposed to be cold. So basically what we have done is that during the monsoon, dt by dy changes the direction. That's very important for dynamics, as you can understand. And we now have westerly winds over equator, unheard of in fluid dynamics. In a rotating planet, it is hard to get that. So just keep that in mind. And the convergence zone really moves here. So that is why scientifically it is a big challenging problem. It is also challenging for models to simulate it. But the reason monsoon has been so much interest is, of course, about 1 billion people live in India, 1.2 actually, from the last count. And India's GDP actually depends upon rainfall. There is a relationship. As a matter of fact, an earlier Prime Minister had said that the Indian budget is a gamble on monsoon. And that's the sort of the one of. And the reason is very simple. Although, by the way, 50 years ago, agriculture was basically 80% of India's economy. But with the high tech and all the improvements and the industrialization, now agriculture is only 13% of the GDP. But labor force is 49%. So when there is a monsoon drought, it's a huge problem for India because there's such a huge amount of labor force that is involved. So I think that's the reason it is important, and that's why we have been trying for a long time to predict it. So I'll give you a quick history of what has been going on in India for prediction. Some of you, so of course India was under British rule, you might remember, since 1850. The British found out that we really need to understand monsoon if you want to continue to rule India. And so they appointed a meteorological observer, and he was called Blandford was his name. And soon after he came, India hit a huge drought. Not just ordinary drought, famine. 6 million people died. Can you imagine? We're now worried about like 200 people, 8 people with this hurricane, that hurricane. 6 million people died. Also a lot of people died in this, and I'll tell you, yeah.
You know how many people lived in India then?
Yeah, I was just going to say, it's a very good fraction. I was trying to just think about that today before I come. Gee, that must have been a big percentage of this. Oh, by the way, those days, India was just not India. India, Bangladesh, West Pakistan, they were all one India, huge disaster. And then government, and there was so much criticism that government said, stop giving forecasts publicly. So they become confidential. Okay? So this has been going on for a while. Okay? And this Blandford guy, by the way, he's the first one who had found a predictor. Predictor is snow over Himalayas. So he will ask all these Indian young people to go to Himalayas with big sticks and measure snow, the depth of the snow. And he will plot the depth of the snow. So the snow-monsoon relationship was the very first one. And again, it was revived in 1972, 75. I'll tell you more about that later. So they used to use that as a formula, but they discarded it in 1960. I was looking at the history of monsoon forecasting, and I see the guy who was in charge. Because they used to have these regression equations, and they will keep changing every year. And he said, snow has lost its power. So then he just dropped it up to that. Well, then actually after that, 1886, now they started issuing the forecast again. Now they started issuing 20-page forecasts. Can you imagine? They have no idea what's going on to the global circulation. The forecasts were 20 pages. And guess what? 1899, another huge drought hit. Okay? And anyway, then the British found a very brilliant guy. His name was Walker. All of you meteorology people have heard the name Walker. And he was a mathematician, senior wrangler, and he was sent to India, find a way to predict Indian monsoon. And then he took India's rainfall and correlated with every place in the world. And that's how he discovered the southern oscillation. That's how we heard about. By the way, I think just to honor him, I'll show you his picture. While correlating India's rainfall with everything in the world, and at that time imagine, what was in the world? The world where he had the data, wherever British colonies were. But luckily, British colonies were everywhere. So they got the data from Australia, they got from Southern America, they got Tahiti. So anyway, so this is a jigsaw puzzle that we discovered. And today I'll show you, and let me just give you now that this oscillation is now, we know, is totally related to El Nino, which he didn't know, and nobody knew, and that's one of the problems. So there is a region, by the way, but his forecast had no skill after some time it was done, okay? And I think that I have to thank our friend Paulino, who's sitting here, because I think he did some calculations with me, and we found out why Walker failed. And look at this carefully, because this is important. So if you plot Indian monsoon rainfall and take all the very high rainfall years, composite them. By the way, when you don't have a lot of data, you don't have models, then you do composite. When you have a lot of data, 100 years, then you do correlation coefficients. But composite gives you ideas about, and this was a very good idea. It came out of this. So it turns out that the southern oscillation, this is the oscillation I showed you, the pressure over Darwin. the pressure over Tahiti, is actually all the years when the monsoon is very good, which really means high rainfall, that index is really negative. Okay? Very well defined. And opposite when the index is high. If I plotted along this a linear sea surface temperature anomaly, it will be the same figure. So just remember that, although you have to reverse the sign. So what it shows is that they are very related, but here is the problem with Walker and everybody else in India. They are related in June, July, August, September, in the summer season. But the forecasts have to be given in April. Look what's going on in April. We don't know very well. It's really totally uncertain in April. So what Paulina and I did is say, listen, don't take the value, take the tendency. And the tendency is really a very good predictor. And believe it or not, that has been one of the most strongest predictors of the Indian rainfall. And we'll come to that. Now, if you look back, remember I told you the three major droughts, 1877, 1899, then again 1918. What you see is these droughts are very large scale and they persist for the whole season. Now, right away that tells you something about predictability. That means this will be possible to make predictions. And in spite of the fact that Indian rainfall has a very strong fluctuation, you do have large space scale and time scale. So just remember that gives you the predictability. So that's where we stand now. What we do today is that, and by the way, we means I have to just separate now from India, although I work closely from India because me and Tim Del Sol got a big problem with India very quickly, so I'll explain to you. So they keep including regression methods. Some of them are crazy. They will use 16 predictors and use 37 years of data. Then they kept changing the predictors from 16 to 8 to 6 and so on. And I used to talk to the guy who's in charge of the forecast, and he said, look, this is crazy. And Tim Del Sol had written papers that it's total artificial skill, which don't do it. They don't listen. They don't do it. Then 2002, actually, biggest drought, and all the forecasts were totally wrong, and government told the forecasters, what are you doing? And so on. So the guy who was in charge, he actually went to Himalayas. He said, no, he did. This is what he called me. I said, where are you going? He said, I'm going to Himalayas for meditation. We never heard from him again. Anyway, basically, Del Sol and I published some papers already showing. Del Sol actually wrote one paper. He took random numbers and showed that the skill of time series generated by numbering was comparable to the Indian forecast. And when I said that to some of the people in India, they all wanted a copy of this paper. Those who really were not happy with Indian philosophy. Anyway, now we do have regression. And I think that, so that brings it now to, so here is, the statistical prediction is going on, all right? The statistical prediction is going on. And butterfly effect is the dominant theme. Okay, now I'm talking about 19. So I'm just going to give you guys a very quick personal retrospective. What happened? How did we make this jump from limit of 2 weeks to predictability of seasonal events? And it's a personal retrospective, so I'm telling you my part of the story. I'm sure somebody else will tell you another story, which is fine, but since I'm giving the seminar, I'm telling you my story. So, and I think that incidentally, at that time, I just finished my PhD at MIT. My advisors were excellent scientists, Lorraine, Charney, and everybody was saying, oh, Lorraine has said 2 weeks is unpredictable. And I told him, no, but what about monthly means? He said, oh yeah, I never said anything about that. So he encouraged me to pursue this. Charney actually encouraged me to pursue this. So we basically tried to advance that, is it possible that seasonal means are predictable? And basically it has two ideas. One is that even in the absence of boundary conditions, planetary waves are predictable. That's just one concept. And the second concept was boundary conditions of influence. So these two concepts in that period really has been. So let me tell you the first one. So these are very old. So David Strauss, our friend here, he actually had calculated the wave number frequency of the mid-latitude circulation. And what he found was that maximum variance is in the low frequency planetary waves. Look at that. These are very long waves, very slow. That's just a data. Well, what does that mean? If most of the variance is in the low frequency, it gives you hope that when you take a monthly average or seasonal average, there may be some signal, because that's where it is. But the second result that we had got at the same time was that if you look at the predictability, the classical Lorentz predictability, and this is the calculation that said whether it's not predictable beyond 2 weeks, because you see the way error grows, and it basically gets saturated within about 2 weeks. This is a standard predictability calculation. You perturb the model, look at how fast the error is growing, and you lose any predictability, because this one is persistence. Persistence means absolutely dumbest forecast. Every day is same as today. That's persistence. And your model becomes just like that. That's why we say it's 2 weeks. What we have not looked at is that that's only for the synoptic waves. The planetary waves have predictability a lot more. So these two results together gave us the confidence that maybe there is dynamical predictability. Okay? So that's what I meant by that was one reason. The other reason was the boundary forcing. And the story about the boundary forcing is actually quite fascinating. I don't know, I may end up taking a lot of time, but I think I'll tell you. So this is what happened. I'll show you each diagram has a story behind it. Okay? So at MIT, Stammel was there. He was an oceanography professor, the famous oceanography professor. And he used to always tell me that, Arabian Sea is very cold, in the summer monsoon, it gets very cold, because he used to go. Stammel was one of the very distinguished oceanographers. And he's not there anymore, but Arabian Sea is very cold. And then Charney went on sabbatical to Israel. And so MIT sent me off to Princeton for 1 year with a very exalted title of visiting student. So I was a visiting student. And then Manabe, who ran GFDL model, he said, what do you want to do? I says, look, I'm a second year graduate student. What can I do? You just tell me, what do you have? I said, we have models. He said, yeah. Can we test what will happen if the Arabian Sea is very cold? And he said, yeah. So he called his modeling people, and we did an experiment where we cooled the Arabian Sea. So this was in 1975. And guess what? Indian monsoon rainfall, boom, went down. So there was a very simple result, and it became, of course, this was totally artificial. But the point is that at those days, nobody was doing this kind of experiment. So it got a lot of attention. Oh, Arabian Sea SST. Okay. Later on, by the way, we don't have to talk about Arabian Sea. I think Ravi is the last one who told me he's interested in the Arabian Sea SST. It does have some effect, because you're all worried about El Nino, and I'll talk to you about that. And so that was the one result. Then, after doing my PhD, I went to do a postdoc at Princeton. And Indian monsoon rainfall is something I remember all the time. In my mind, this is the way Indian monsoon is, plus, minus. One day, one of the guys from GFDL was walking around in the corridor showing everybody snow data. For the first time in 1976, snow data had come. Imagine snow data, that was 1896. After that, nobody wrote any paper about snow. The sort of except India was using it. But now the first time there was a snow data. He just showed me, and I said, this almost looks like Indian monsoon if you turn it upside down. And he said, really? Yeah. So he took his data, I took my data, and we turned it upside down, and this is what we got. And this just caught like a fire. Indian monsoon is affected by snow, and there are global programs that were launched to study snow and ice and its impact and so on. So anyway, just stay there, okay? There was nothing was happening. Keep that result in mind. And then Charlie, at the same time, was at NASA, and he was doing desertification studies. Many of you guys must have heard. He wanted to know why Sahel drought persisted for so many years. And he thought it was because of the albedo. And he was running that model and tried to look at the internal variability of the model. And he showed, and he found that the model was not very much. Okay. How does he calculate? I'm sure students are going to laugh, because if these days you guys try to do something, I think Raja will say, no, go back. he had only 3 model runs. So his sample size was 3. Length of integration, 45 days. Ignore first 15 days. So you remember how you ignore 100 years and you go, okay, ignore 15 days, take monthly mean for July, find out. But he was challenged, so he published the result. It's one of the very big quoted papers in this. And in the result. And then he got an invitation to go to India. There was a big conference on Monsoon, and he called me one day and he says, look, I don't work on Monsoon. I don't know what I'm going to talk about. I said, well, that's very good. I said, I don't know. So I just told him 2 things. I just told him this result, that SST affects Monsoon. And then I told him snow affects Monsoon. And then he started sort of pacing the corridor, and then I said, gee, he's thinking about something. And then he said, and guess what? Random numbers don't affect Monsoon. He just found out. In other words, random perturbations that he made, they don't affect Monsoon. So you see how early we're going? So we already had, between our results, a signal due to the boundary conditions, and a noise, and the signal to noise was very high. That's basically the origin of this basic idea, that how did we get, I mean, now we understand much better, by the way, and I can tell you, but that's really the origin of this idea, that just the fact that we have very simple evidence of the boundary forcing on the one set of results and the random variations. So now we understand very well, if you have a temperature anomaly, it creates a heating anomaly, and then heating anomaly creates a circulation anomaly. Now it's this is a standard model, we do that. So I better run to the actual estimates. So people have estimated monsoon predictability. Many people have estimated. For the purpose of students, this is my favorite diagram, because I told you, there's a signal, there's a noise. When you're talking about seasonal predictability, it's not weather, like this will happen. You have a signal, you have a noise, and the way you do that is that you run the model many times with random perturbations, and you calculate the variation. That's called noise. But then you have many years of boundary conditions, and get the mean of this, and then you find the error standard deviation. That's the same. That's the signal to noise ratio. There's a very nice mathematical and statistical formula that you calculate the signal, noise, and the ratio. That ratio gives you a measure of predictability. Okay? Many of you have done. Those who are taking Climb 751, you have to do it. They're in class. And you do that. And this has been done. In fact, Zhao Yang and one of the students were there in Trieste, and they calculated for 4 models, and they found very high predictability in all the tropical atmosphere. In the monsoon, Del Sol took like 6 models. Everywhere it is yellow, just don't worry about the numbers. If it is yellow or above, highly predictable. That's the conclusion, that these things are highly predictable. So, where do we stand then about predictability? We find the predictability is very high. But on the other hand, I told you that all the models, all the empirical methods that were using this, and FNSST before the monsoon surge, they had no predictability, they had no skill at all. So why the predictability was high? Very simple. These models must have some way to be able to predict the sea surface temperature in future. So you are starting the model today, but you are able to predict it in the future. And turns out that is actually what is going on. And by the way, all those droughts that I showed you, they were all El Nino years. They were all El Nino years. 1877. This was the SST anomaly. The only problem is that we could find this SST anomaly only now, after the data, shift data was analyzed and processed in the last 30, 40 years, we have got. So big El Nino years are the ones that gave you. So just keep this in mind, that the simple conceptual model, you have to understand droughts. Why droughts happen? It's a very simple conceptual model. You have an annual cycle that has a rainy season, and I showed you things move, then you shift it. Then you get a drought at one place and flood at the other place. That's the simplest conceptual model. Why does it shift it? Because of boundary conditions. So I'll give you one example, okay? So but just the basic descriptive description you should keep in mind, and how boundary conditions will do that. And look at, I chose one example. This is a normal SST anomaly, okay? I showed you, this is at the beginning of the class, very warm. But if you look at the warm El Nino years, this warm place just shifts. Okay? So the whole ocean now is much warmer here. Okay? And same thing about the rainfall. This is the normal rainfall. Now, for these years, the rainfall shifted. Do you see that? So it helps to look at the total rainfall field, because what you are doing is you are sifting the climatological annual cycle, and you are getting out. What we normally do is, because we like color graphics, and graphics you can paint, color blue and red, we always show anomalies. So this minus this is this. And this looks very good. Oh, you see, so there is a shift, there is a dipole, you get a very large precipitation, you get a deficient rainfall, and now you can do a lot of theory based on these heat sources, anomalous heat sources. So just keep that in mind. If you look at the India's rainfall for more than 116 years, I think, oh, this is about 136 years, you get a very simple relationship. Everything that is red is a warm El Nino year. Okay? What do you see? Almost all the red dots are below. They're negative. Every time it is blue, that's a cold El Nino year in Pacific. This is the kind of information India and Walker didn't have. And most of them were actually blue. But not all. And that's the purpose of talk today. Is, okay, we know that part. And we can think we can get our models. Now, how do we get exceptions to that? That will be really the topic that I'm just going to cover. Oh, by the way, Ravi and Boha calculated. So this is just, it gives you an all India rainfall. What is the structure of that correlation? This is a correlation between the El Nino, tropical Pacific, and the rainfall. So you see, what happens is that it's not just India's rainfall. It is a huge band, very large band that is stretching, okay, of the positive rainfall. And then there is so this is the point where I want to tell you is that, yes, there are a billion people in India, and we're concerned about them, but there's nothing special about India. I think it is part of a very large scale. And when we talk about India's rainfall, we have all kinds of problems now that we'll explain. So that is what, now it is beginning to introduce to you, okay, what we are getting at, why the problem of India, we are going to try to predict. By the way, I just put this, I'm not going to talk about it for students, because you may be asked for mechanisms, how El Nino affects monsoon. So there's a lot of analytical work, simple theoretical work. None of it actually shows, because the things are so complicated, but it is something to know that there has been a lot of thinking on this question people have given. So I'll come now to the actual prediction that was done. It was published by the Bohla et al. Paper by using a CFS model. And I think it gives you all the descriptions. It was done for 58 to 74. What is special about it? All these results that I have seen till now, they always do 79 to 2014. Why? Because that's the initial data that was available. So Bohla and Chilsu, and they really worked hard to get all the initial conditions and did the prediction for 50 years. That's what it is, by using CFS model. Okay, now you should know we are using models to predict. How good are the models? That's how good are the models. This is the bias in the model, larger than anything we observe. So it's just a warning sign that we are faced with another challenge. We have the data problem, we have the mechanism problem, we have the model problem. We don't have models, but, and by the way, I can show you many. There's a bias in the rainfall, there's a bias. These are all biases, pretty large biases. Not only in the CFS model, but the other model. So actual values are here. The model goes up. Look at the amount of bias. Some models have huge bias. Keep that in mind. This is the model, that's all we have. We have to work with that and try to understand predictability using. Luckily, you still, well, actually, I think I have a slide that said, yeah, climate models, good luck. Just remember that. In spite of the fact that models have huge bias, we are actually able to predict fluctuations on top of the mean. Okay? So mean has a huge bias, but the fluctuations, we are able to predict. And one example is, this is again Bohu's paper for the entire 58 years. Many of the El Niños you can see here were reasonably well predicted. I'm just going to run through this. I'm sure you have seen this before. Those who have not seen this before, just it is an example that we are doing well in predicting fluctuations. Okay. If you look at the actual data on the tropical Pacific SST, by the way, what we call Nino 3.4, every time I say Nino 3.4, I have actually another map which comes later, shows you, it's an equatorial Pacific SST, that area we have just called. Okay? And this is the observed and forecast. Look at that, pretty good forecast. Pretty good forecast. And if you take a 21-year and 1 year, there's not big difference. But let's go on to the fact that, so we have a model which does a good job. If you look at the period 58 to 78 and 79 to 2014, very similar. I'm saying that just a one-line conclusion. There isn't a big difference between the early periods, which is important because we were afraid early periods have not good data. Data is a big problem, but it doesn't seem to be our ability to take advantage of the better data is not there. That's the reality. But there is one difference. And that is that if you look at the observed, see, look at the forecast, black curve. They're almost same place. Look at this. It cuts the apple here. But look at observed. It's completely different in the earlier period. What does it mean? Our model doesn't change. The nature changes. But the other way of saying that is that nature's changes in the characteristics of El Nino are not captured by our model. Our model continues to behave exactly the way it always behaves. So we just do not have that ability. That's the big limitation of the model. Okay. And now coming back to the question, we wanted to know the Indian monsoon. What is the Indian monsoon? And Indian monsoon predictability is not too bad, but it is 0.3 earlier. So you say that's not a big thing. The good news is it's much higher than zero. Okay. Because almost all the methods I showed you, empirical methods, the skill was zero, by inches. So this is a big news. This is absolutely the big news that, okay, now we have models which have skill. And in fact, I got a chance to compare. It's not easy to get data from India to compare, but they gave me 88 to 14 data, what they were predicting, okay? So they gave me, and we calculated their correlation skill was 0.26. This model, just for this period, was 0.42. So I think there's no doubt that the models now have reached a level where they are much better than empirical methods. So if there is one actionable conclusion of this is that, although India will never do it, but I'll say this will drop their regression models. It's just, it absolutely has zero skill, but that's what has been going on for 125 years, but they probably continue to do that. All right, so that's the status of our seasonal forecasting. Where is the challenge? And that, to define that, I'm going to tell you about, pick up those 2 years out of this period, 72 and 97. Why those 2 years? Now each year has a completely different story. And I can tell you, first of all, nobody had ever done prediction of 72 in this, because all the predictions were done for 79 onwards in such a detailed way. I'm looking at the monsoon. 72 El Nino was a major El Nino. Those of you who are keeping track of it, the fisheries collapsed completely. To me, it is interesting, this story, from the following point of view. All the students here now know what's going on in El Nino, right? We have a climate discussion, right? And you know, and you get maps, and everybody tells you what's going on. But guess what? In 72, I was a graduate student at MIT. All the world's greatest weather and climate scientists were about on the same floor and one floor up. Nobody had heard of El Nino. That El Nino was raising in the Pacific right at that time. Okay? Nobody had heard of it. I actually so happened that 72, I had to go to India, and I went to my village, and my village completely depends on agriculture. And everybody was complaining, there's such a huge drought, there's not enough food. But we had no idea why. because we didn't have any SST data, we didn't have any information. So when this model started working, I thought, all right, let's do some prediction. Okay, what about 97? The reason I chose 97 is because look how similar it is to 72. Just as big an El Nino, okay, as 97. But in 97, all the data was there. It was such a major news in the world because El Nino, it was predicted well in advance. Everybody was talking about it. World Meteorological Organization had a big conference in August, and all the media was all covering El Nino, the biggest El Nino ever, and they kept pushing this story till 31st August, because the conference ended on 30th August, and all the media was all excited about El Nino. 31st August, they dropped all the stories because Princess Diana died. So all the stories about El Nino were thrown out. But here is the big thing happened. India really wanted all of us to give them the forecast. And we were so certain, absolutely, this is the biggest El Nino, there will be a drought. Well, guess what? There was no drought. So that's the second part of my talk, okay? So that is why I picked up these two cases, okay? So just to tell you that both El Ninos in the ocean, very similar, as you can see that. Both El Ninos evolution, you see, this is for 72. Look at that, very well predicted. These are results, this is model. This is how well predicted this evolution. 97 also, very well predicted. Very similar El Ninos. India rainfall, 72 minus 23%, 97 2%. So you see, that becomes a topic then. Okay, so what happened? And as a matter of fact, this is it's kind of a okay. So I'm sorry I've taken too much of the time because my real talk starts now. Okay, so this is really the real talk about something that is what we have done, and I'm going to show you. But before I show you results, and I have to ask you to train your eyes. I'll show you what I mean by train your eyes. Rainfall over India is available for 116 years, but only over this part of real estate. No ocean data is available before 79. Okay? Land data is available. So see what happened in 72. If you took a bigger land area, then you can see that. You see that Indian drought, right? And you can see that. So many of the maps I'll show you a large area, but imagine that we are limited to the data over India. When you look at the forecast and observed and forecast, so forecast is of course a model, so it has ocean and land both. So therefore you get all these new things with everything. But if you concentrate on the land, it's absolutely fantastic forecast for 72. So what does it mean? If we have the same model we have today in 72, we had all predicted it much better.
Can I ask a
Yes,
clarification? Maybe because I don't understand.
Yes.
I don't see the link between the snowpack and the El Nino and monsoon.
Oh, okay. So the link between snow and monsoon is a completely independent forcing function, and that is been now put aside for the following reason, because of global warming. Snow is so trend; it has such a strong trend that we don't. So in fact, I had another slide. So snow-monsoon relationship is a topic of huge research that was going on and is still going on. 20 numerical experiments. Now we don't get much because the actual data of snow has gone. El Nino is the one that I'm going to talk about, and I showed you the relationship. Warm El Nino, when it is warm, those are the years when it's a drought. And I showed very quickly the mechanism, how the forces in the tropic heating produces. Now I'm going to show you the result, hopefully where those mechanisms are working. But what you find that they're not really working very well, so that's why this remains a challenge. But so there are two different issues, and then there are a couple others which I'd like to introduce about the monsoon forecast. So the 72 was absolutely so this was the forecast. Now I'm just showing you that area from the model, although it's a global model. I'm just showing over India. Pretty good forecast. But you may say, well, is it possible that it's a sampling problem? By the way, so if you do numerical experiments, you can get by sampling a wrong result. So we did 20 times. So we do a 20-member ensemble. So then we looked at each ensemble member separately for both 72 and 97. And guess what? All the ensemble members were giving almost the same result. What does that mean? That means it's not a sampling problem. Although I can tell you that as we talk, I think Ben Cash is giving a talk at College Park, conjecturing that maybe if I have 100 ensemble members, it could be one of them will be okay. It could actually have gotten the result. So that's the challenge of signal to noise. Okay. So I think that this is what, when I said discussion, I really mean that let's now go over what's going on. What is the reason we actually are unable to predict the subtle differences between the El Nino monsoon relationship? We already showed you that the big relationship we have already captured, okay, about model. That's a great progress in the modeling. So I think that let's start by looking at the ocean temperature. So this is the model's ocean temperature in 72. This is 97. If you look carefully, warming is not very different, but the Indian Ocean is quite different. You say, haha, that's the reason. Indian Ocean is the problem. And not so fast. This, what you see in Indian Ocean, is not the forcing. That could be response. Because when you have a weaker monsoon, you get colder SST. So what part of the Indian Ocean is actually the reason I'm going to emphasize in that? And I'm going to show you. Because so, see now, from now, you have to just act like you're working on a thesis topic or a research topic. You start asking yourself, so how do we explain this? Well, let's go back to our zeroth order model. What was our zeroth order model? Our zeroth order model was that if you have a SST boundary condition, it will create a heat source. And that heat source will change the circulation and rainfall. Okay? That's our working model, and you can do it model. Is that what is happening? Let's look at it. So is it possible to say, now Strauss and his student wrote a paper about 97, and they said, yeah, that's what is happening. They took some kind of a diagonal heating field, and they found that if you have these 3 fields, then you actually get the 97 observed result. But if you have just 2 of them, then you don't. Okay, that's the simplest way to describe, okay? If you have just a dipole, if you don't get the 3rd heat source, well, what about our model? See, well, by the way, we have not saved the diabatic heating field. We also tried to get it, but we don't have it. And David is trying to get there. But we have precipitation field. So let's say it's like a, poor cousin of the heating field. So now, here is the difference. Now, just remember this. I'm going to put David on the spot here. Here is a difference between, this is a very big difference here in the Indian Ocean, right? See that? Big dipole. The question is this difference as much? Now, if you look at carefully, and you can see that I'm on slippery monsoon water here, but you see, there's a big heat source right here to the south of India, and there's a big gap here. Okay? So, I mean, I can still try to support David's result through GCM. But still, that's not the complete explanation. So let me just go further. So let me summarize everything I have said till now. What we have found? We found that the SSTs are different. The rainfall predicted by the model is identical almost, but the data was completely different. The observations were very different. So what went wrong? So maybe there are other factors other than El Nino. Let's look at that. So let's first, by the way, this is the way you have to analyze any problem. When you are not getting, understanding what's happening to the predictability, you look at the modes of variability. What are the most important modes of variability? Are you getting that? So if you do an UF analysis of the Indian rainfall, your UF1 for a very long data set, this is an El Nino response, but you get about 15%. The second mode, where you have a lot of rainfall here, only you get about 8%. The thing you need to notice is the second one, it has a huge trend. This is actually a secular trend. So if you do UF analysis, And by the way, I can show you the next figure, then you will see the UF1, and if you correlate that with the tropical Pacific SST, you get El Nino. So you know that UF1 is the El Nino. UF2, we don't know what it is. We are trying to understand, a lot of theories have been given, but I showed you that UF2 has a huge trend, a 50-year trend. It's not global warming. Global warming signal has been removed. Some people are claiming that it is the aerosol effect, which I don't believe, but that's one GFDL model. I believe maybe it is the Indian Ocean warming that is taking place, but this is something we have to understand. But that's because I do an UF analysis. But there's another method to analyze, and that method was actually used by Krishnamurti, who's here in the lecture hall. And many of you know he has done a lot of multi-channel singular spectrum analysis. The advantage of this method is that you get persisting patterns, but also you get patterns with period and structure. And he actually got two seasonally persisting modes. ENSO and IOD. Oh, I didn't expand it. Indian Ocean Dipole. Just remember that. So ENSO is the tropical Pacific SST, IOD. So Krishnamurti has shown, Krishnamurti gave me this data, that the ENSO mode actually, rainfall, so this is OLR, which is the same as rainfall, by the way, is related. It has a very, almost you get a lot of, you can remember this picture is very much what I showed you for the model. And this is the dipole. And then he looked at the forecast in the CFS
Shukla,
model.
is this rainfall or SST?
It is OLR.
So it's rainfall.
Rainfall, that's what I got. Yeah, OLR, yeah, so rainfall. So this is like, high rainfall. So now, look at his predictability. ENSO mode is highly predictable, just 0.6. Just like I showed you, the ENSO was highly predictable. But the IOD mode, zero predictability. And he looked at each ensemble number, all of them, it was zero. So there is already a suggestion. And so, I'm sorry, I should have shown this diagram before for to define. So when I say Nino 4, this is the SST, that we call it Nino. And this box is, we call it as IOD, the difference between this and that. Why I want to show this, I superimpose this on top of an actual SST anomaly field. It already had the signature of IOD. So El Nino and IOD are very difficult to distinguish. That's all, I just wanted to keep this in mind. Okay. But this is a figure that really interested me. I have not seen this before, because we have now 116 years of data, thanks to India, they gave me. So if you look at the 30-year correlation, you see El Nino and monsoon are very strongly related, significance level, minus 0.6. Although they're getting a little bit weaker, okay? But still highly significant. But look at IOD, zero correlation all along, just like the CFS model. But there is some indication that IOD has become some kind of a forcing function for India's rainfall. And this is, I want to pursue that now in our model. So I take the ENSO index and I take the IOD index and correlate that with the model rainfall. And so this is for observations, observe El Nino and observe rainfall, but only for the period, 79, because that's the only period we have. This is the model El Nino and model rainfall. What do you notice? The first thing you notice is that the model is going gangbusters. Every El Nino is a very strong El Nino. The rainfall is a very strong rainfall. As a matter of fact, if you try to verify model El Nino, observe in real data the correlation is 0.5. In model is 0.88. That means it over predicts the rainfall. But if you do the same thing with IOD, then you begin to see the problem. So this is where one of the mysteries that we're trying to find is, this is data. The data IOD, the Indian Ocean, is the correlation with over India. You see there is some positive correlation here. Okay? And I have to tell you a small story. So I showed to Ravi, I said, look at that, this is a positive correlation. And he asked me, what's the value? I said, 0.2. He says, useless. Why are you looking at it? I said, Ravi, why are you being so tough on me? And then he told me that, 6 months ago, he had brought some correlation that was 0.25. And I said, that's useless. So he's like, so anyways, there's a lesson there. So really just remember that. So anyway, I'm glad Tim Delsol is not here because he might have walked out of protest. This is the problem with statisticians. They didn't tell you what to do. They just tell you what you cannot do. So, I mean, they only tell you it's not significant. No, I don't believe it. I have felt, showing that and all the India's, by the way, there are about 8 papers published in the last 10 years. 8 papers published showing that the IOD produces positive rainfall over India. Okay? Especially the positive mode of IOD. So that is what is reflecting this here. And this is the IOD. You can see this IOD. Well-defined IOD in data. Not only now, but you see this? There is an IOD, so it's not a fiction. And it does have indication that it will give. Model has an absolutely fantastic IOD, absolutely opposite rainfall over India. And in fact, what I'm going to tell you is that this IOD is in nothing but El Nino. So model is so overwhelming that it just demolishes IOD completely. So the important role that Indian Ocean would have played, so by the way, I've just taken down to make it small so that you can see so clearly now that look what is happening in observations, and look what is, in the Nino relationship has a negative correlation. IOD has actually positive correlation, but we are not able to capture it by our model. So I said, okay, in spite of what Ravi told me, and in spite of what everybody, Tim Delsol said, no, there's no segment, I'll just do composite. Take all the years in last, 58 onwards, where IOD was very strong positive, because that's what we expect India to have positive rainfall. And this is what you get. You get a very clear signal that, and these are by the way 10 years. Okay? You get a very clear signal that positive IOD produces heavy rainfall over India. Then you realize that if there is a big El Nino, that will dominate. So can we remove the big El Ninos out of these 10 years? So out of these 10 years, there were 3 big El Ninos. You remove them. Then you get this. It's a very large signal of the IOD. So this together, so I'm beginning to now close my story. What is the story? The story is that El Nino in the model has such a strong influence that it kills the IOD possibility of mitigating the El Nino effect. So 97, that probably, Indian Ocean was important. This is sort of, so I'll show you a few more figures, but that's where I'm going with this story. So I think that, oops, oh, okay, so I couldn't, no, okay, so just, oops, so just remember these big conclusions that I'm drawing from the model results. Model predictor and senior answers are too strong. See, observed correlation is 0.5, model 0.88. What I didn't show you is that UF1 of the observed is 15%, model 33%. So model just absolutely El Nino dominates the model. Then when you come to IOD, it's actually opposite to observation. So it's not only it doesn't help, it hurts. So IOD, so therefore this possibility that 97, as Strauss had conjectured, that maybe the Indian Ocean was a very important player. At least it suggests, the only thing we don't know is that what was the actual diabatic heating theory? We don't know that very well. So I think based on that, let me just draw. I know I'm just running out, but this is my last slide. I just want to draw just the basic summary. By the way, this is an important point to remember, is that our models have huge bias. They're very much in error, yet they're able to predict perturbations superimposed upon the mean. That's an amazing thing. And I think that we are able to predict Indian monsoon, but it is entirely because we are able to predict El Nino. Nothing to do with the monsoon depressions, intra-seasonal fluctuations, monsoon, what goes on in monsoon. So you can imagine, just El Nino, that's what is able to give prediction. And I think that what the data shows is that when sometimes El Nino effect can be mitigated by the Indian Ocean, model cannot capture that. So if El Nino comes, boom, you get it. So that's what probably happened in '97. Okay, and I think that this is, of course, another conclusion is that we are not able to take advantage of better data. This is an important point. Why? Because that means our models are not good enough to take advantage of good data. Because it's only when you have a model is much better, you take advantage of good data. Same thing happened with weather prediction. Weather prediction improved only after we learned how to use satellite data. Okay? And then we could actually improve the weather prediction. We are in that stage now, in the climate prediction. But the last point I want to say is that, and that's most for the scientific research scholars, I think that it's important to be able to study individual cases. And you have to just go into the detail and try to do numerical experiments to understand. And by the way, come and think about it, so Bohu and Chulsu, we are planning to do a numerical experiment to see if we mess around with Indian Ocean. I'm not telling you what we'll do, so that's why I'm just telling you. But we're going to mess around with Indian Ocean and see, can we either improve this result or can we degrade it? So that does Indian Ocean, because this is something that we had always, this is what we're going to do. All right, but thank you very much. I'll be glad to ask any questions. Yeah.
So is the argument for why the Indian Ocean dipole is becoming a more prominent signal in the Indian Ocean SST because of climate change, or do you have an argument for that?
That's a very good question.
Yeah.
And you remember I showed you the trend in the rainfall, and and also showed you the structure. It was the warming of the Indian Ocean. And this is a question that I'm actually right now asking. Is it possible that, by the way, the warming that I showed you of the Indian Ocean, that was on top of global warming. I forgot to tell you that the global warming signal was removed. Of course, the way the global warming signal was removed, a little bit unusual. Many times people remove the trend. What we did is what Mike Wallace does all the time. Take the global mean temperature, and remove it from every data point. But it's global mean. So that way, what you are removing has no spatial structure because you are removing constant number from every big point, global mean. So the big global mean was already removed in the SST. What was left still had an extra warming in the Indian Ocean, which makes sense. Yes, Krishna.
Yeah, the point you just mentioned, isn't it possible that Indian Ocean is warming with a different trend compared to other global oceans?
That's actually the UF2 that I showed, and this is a change in the rainfall. If I had shown you the UF2 of SST, just like that, it is warming. So
Yeah, right. But when you use the Wallace method to remove global change,
yes.
and then claim that you have removed the global change trend from Indian Ocean, that's not entirely correct.
Okay, so we are now being a little bit sort of semantic. What I'm saying is that there is a global warming trend, but on top of that, there may be a regional warming trend for the Indian Ocean. Let me put it that way. Indian Ocean is warming faster than global ocean.
Right, that is the point.
That is the point, yeah. And that's what I wanted to say. So if it didn't come out that way, but that's, yeah.
I have another question.
Yeah.
Before we sort of, it's an important point that you made, that we need to see whether Indian Ocean is the problem in the model prediction. But in addition to that, we also need to understand what's happening in the nature. In the nature.
In nature,
That is the relative influences of Indian Ocean dipole and the ENSO on Indian monsoon. That's not well understood.
I tell you, in fact, what I showed you today, to look at the Indian Ocean dipole over 100-year period. I've never seen that before. So in a way, if you look at the first 50 years, there's absolutely zero. There's no relationship. So something is happening in the last 30, 40 years. And that's where the suggestion comes. It has to do anything with what is going on. But it's the problem. I mean, Krishnamurti has written actually, I saw your paper, by the way, and it's clearly there is a problem. In the model, there is a huge problem. So that's not a question. The question is, how do we analyze the observed data to be able to detect the Indian Ocean? And this was my first attempt. Take all, take all of them, highest values, and then take out the big El Niños. And it suggests that there is something that is significant. But it will not pass any significance test or something, I'm sure. So it's just good for understanding. Yeah.
Looking at that, is there any geographic barrier for ocean circulation in the Indian Ocean that kind of makes that SST different because of circulation of water in the ocean?
Oh, no, it's not. It's actually, it is a product of the ocean dynamics. And in fact, Boho Wong, who is here, he has done a lot of experiments on the, with and without interacting. So it's not a barrier effect. It is a dynamical effect. It's basically, it has to do with the ocean waves propagating and reflecting from the African coast. Okay, it's just a basic ocean dynamics that dipole is creating.
Yeah, the other question I have,
Yes, go ahead.
Is there any for the drought and in El Niño, it reach 5 to 7 years? Is it like building dams for the drought seasons? Or
I have confined my interest to season and predictability and so on. I think that the decadal predictability is a big uncertain question, but you're right. A lot of people are asking the question because big decisions that society has to make, whether to build a dam here or build a dam there and so on, will depend upon some idea about the. So there, what we're doing is that we're trying to estimate the probability of more El Niños, less El Niños. That's all. Not individual El Niños. For every phenomenon, we have two limits. One is limit till the life cycle of the phenomenon. So you're predicting a hurricane, you can predict for a few days. That's the life cycle, so long as 3, 4 to 5 days, 10 days, because you can do it. If you're predicting El Niño, you can predict to the life cycle of 3 months, 6 months, and after that, 8 months, you lose the predictability. Okay. Once you go beyond that, all you can do is PDF. That the probability distribution can change from one 50-year period to another 50-year period. So that's what his research is going on. We're not very confident. At least I'm not able to tell, although there are a lot of people working on it. You have your hands there.
Yeah, what would happen if you got rid of the Himalayan mountains?
Oh my God,
15 years ago, there
I
weren't
was
any.
hoping somebody will ask this question. So I have done that. Okay. No,
A feat, truly a feat.
Yeah, well, when I say I've done that, so there is a BBC documentary where it starts out by this statement. Dr. Jagadish Shukla just removed the Himalayan mountain. But the reason is when I was visiting Princeton GFDL, Manabe, which I work with him, we did this experiment, remove the mountain completely. And what happens is that the monsoon becomes very weak. So I wanted to make this point right in the beginning that Himalaya has a big role. And I mentioned this word, but I'll explain it, not only because of its barrier effect, because it sits there like Himalayas, and all the air that comes has to go around it, right? All this. But also it has a thermal effect. Imagine stick a heat source right in the middle of the atmosphere. So it has a huge, it gets the monsoon very, very weak in this. And in fact, but it was all done with atmospheric model. And if some student has the energy, it needs to be done with a coupled model. It hasn't been done with a coupled model. And in fact, I told Manabe, why don't you do it with a coupled model? But he has gone on to do global warming calculations now. So that's a very good question. And there is a whole group in China that study the effect of Tibetan plateau, and they do all kinds of experiments. Good question, good geology and climate question. Yes.
So
So at the beginning of the talk, you sort of suggested that you hope that the monsoon prediction would rely more on modeling.
Yes, yes.
But near the end of the talk, you sort of suggested that the models are over emphasizing the impact of El Nino that we're not capturing, especially in the recent decades that the IOD seems to have a bigger.
Yes, yes, yes. So that sounds contradiction.
Yes, so do you think
Let me
that?
clarify.
Okay.
Let me clarify. First of all, in spite of all the models problems, they are better than that's number one.
Okay.
And when you have a bias like that, you can correct it. You don't have to. So, and if you, by the way, I didn't show you, but if I did corrections in the forecast, in a kind of a specific way, it could have get better. So my statement, I stand by my statement. What I was trying to say is that that's not going to solve the problem, because you still have problems. But even now, with the current problems, much better than the empirical methods that are being used. Yeah.
You mentioned different droughts, and so
Yes.
how do you define a drought? And is
Okay.
it only during the monsoon
Yes.
season?
Yeah.
And how long do they
Yeah,
last?
so that's right. So this is India has a very well-defined, India is a bureaucratic society. So for everything, there is a manual. A friend of mine said, they have all kinds of manuals. So they have written down the definitions. So there's a percentage. So if all India rainfall average over JJS, that's the monsoon season.
So the
is
4
less.
months.
That's 4 months. That's the main rainy season. And then there's a drought, severe drought, moderate drought. So they have a drought, but they predict only above normal, below normal, and then the drought. So it's basically 10% and 20%.
I see.
And
10%
10%
is drought.
is basically, 10% is normal, because that's the standard deviation. So the all India rainfall that I showed you, the standard deviation is 10%. So they used to say, oh, it's normal. And they say, see, forecast was good, because their normal was 10%. So we made a lot of noise. I said, you guys have defined your metric such that you look good, 10%. So now they have changed to plus minus 5%. So if it is above 5, but to get a drought, you have to go above 20. So you remember I showed you the numbers for some reason, minus 23%. 87 minus 29%. That's it. It's a working bureaucratic definition, because as soon as that hits, you can imagine government policies get into place. How much aid a state will get. Just like declaring emergency here, right? As soon as you declare emergency, the government aid starts flowing in. So India also has defined these things. Same thing with onset of monsoon. They have a date, they have a definition and a date, and if it's delayed, government has to help that which has been delayed. It's not a very profound definition, but it's a working definition. Yeah. The students have no question, I'm sure. It's totally clear to them, right?
I have a question.
Yes.
If you want to ask a question.
Yes.
So, earlier in a slide, you said that the SST affects the monsoon and the snow affects the monsoon, and then Charney did an experiment where he showed that random numbers do not affect the monsoon. And I recently read a paper by Hasselman and Frank Wignall about how they used Gaussian white noise to characterize atmospheric forcing. So I was wondering if the random numbers that Charney discovered don't affect the monsoon could be related to atmospheric forcing.
Okay, so I should explain. That's a very good question. First of all, let me tell you what Hasselman paper you read.
Yeah.
That really is saying is that this ocean, because of its heat capacity and the way it integrates the atmospheric fluctuation, can generate SST anomalies even by the random atmospheric forcing. So that gives you the mechanism, one possible mechanism to generate SST anomalies. Everything we are talking about today takes for granted. Those SST anomalies have been generated. Now what they will do to the atmosphere. And what Charney was saying, and maybe I didn't explain, once you have some anomaly of SST, albedo or whatever big forcing is of snow, then the influence you can calculate by a model, so long as if you randomly perturb the atmosphere, that effect doesn't get much larger than the effect of the forcing. Did you get that?
Yeah.
So that's in that context. So what Charney was doing, He was looking at the effect of albedo. So he changed the albedo and looked at what will happen. But then he didn't change the albedo, just randomly perturbed the atmosphere, and he found it is not changing the result. The result remains same, with and without albedo. Just like the paper you were reading about the SST.
Yeah.
There. Whereas the Hasselmann concept is just to say that the atmospheric random forcing can generate ocean SST anomaly. So that's, he's trying to understand the mechanism to create SST. Charney and what I was talking about, given the SST, given the albedo, given any of these, how do we decide whether it is predictable or not predictable? Is that clear?
Yeah.
Okay. Okay. All right.
Yeah, do we have any other questions for our speaker? All right, let's thank the
Okay, thank you.